So let's begin with a little bit of review of what we covered in the last lesson. The local extremum between zeros theorem states that if I have a polynomial with a degree greater than that or equal to 2, if I have multiple zeros that occur, there has to be at least one local maximum or local minimum between those zeros. So as an example, if I have a graph that looks something like that, I have 3 zeros right here, and right here. Therefore, I have to have at least one local extrema between those zero values. In this particular case, we see a local maximum there and a local minimum right here. There could be multiple local maximum or minimums. If I have this type of function, I have 2 zeros in this particular case, that right here and right here. But in this case, I have 3 local extrema between those 2 points. I have to have at least one, if not more. We also discussed that when we have concavity, where it changes from a concave up to a concave down, or vice versa, that is known as an inflection point. For polynomial functions with degrees greater than or equal to 2, we know that there are at most n number of zeros. If I have a cubic function, the most number of zeros that I can have is 3. If I have a quadratic, where x squared, the most zeros I can have is 2. I don't necessarily have to have 2, I could have fewer than that, but that is the maximum number of zeros that I can have. Along with that, there are at most n minus 1 local extrema. So if I have a quadratic and I graph it, I could have up to 2 zeros, but along with that, I only have 1 local extrema. It's 1 fewer than that. That is the most I can have. I could have fewer, but that's the most. There are at most n minus 2 points of inflection. Since I am changing from concave up to concave down or vice versa, I'm going to have n minus 2 at the most. So a cubic function is going to have 1 inflection point at most. And then concave up versus concave down. If we have 2 points and we draw a secant between those 2 points, if the entire secant line is above my graph, then that portion of my graph is concave up. If the entire secant is below my graph, then that portion of my graph is concave down. If it crosses over my line, my graph, then that means that I'm neither concave up or concave down. I've switched from one to the other. So that brings us to today's lesson. Today we're going to be concentrating on the end behavior of polynomials. The end behavior is going to be very, very closely related to the leading term. Not just the coefficient of that term, but also the degree of that term. And we're going to take a look at that by looking at several different graphs of some fairly similar polynomials to see what we mean. So if I were to graph y is equal to 2x cubed, my graph would look something like this. And you'll notice it is coming up from negative infinity, crossing over, and going out to positive infinity. So my limit as x nears infinity is infinity. My limit as x nears negative infinity is negative infinity. Now let's contrast that with the next graph, which is simply a negative x cubed. If I graph negative x cubed, I am coming from the top, from positive infinity, down, crossing over, and then continuing on down. So as I near positive infinity on my x, my limit goes toward negative infinity. As I go toward negative infinity on my x, then my value of y goes up to positive infinity. So you'll notice that they are opposite. What changed? Well, not only did the 2 change, but more importantly, the sign in front of it. That negative sign flips the graph upside down, just like we covered in previous lessons. And that means that my end behavior is going to be reversed. Let's take a look at x to the fifth power. So we still have an odd degree to our polynomial, but this time it's a 5. You'll notice that it looks very similar to our first graph, that of the 2x cubed. We're coming, as we go toward negative infinity on my x, I'm coming from negative infinity on my y. As I go toward positive infinity on my x, I'm going out toward positive infinity for my y value, the same as the 2x cubed. If we go with x to the seventh, so as I look at negative 1/2 x to the seventh power, you will notice that my graph is flipped. I'm coming from negative infinity up on my y as I get closer to my negative x values, going toward infinity, negative infinity. And then I'm going down toward negative infinity on my y as x increases and goes towards the limit of positive infinity. So here's what we can derive out of this. For odd functions, the end behaviors are going to be opposite. So if I have a cubic, 1 to the fifth power, the seventh power, ninth power, 11th power, if I am coming in from the negative, I'm going to be leaving going toward the positive. If I'm coming in from the positive, I'm going to be leaving toward the negative. Their end behaviors are going to be in opposite directions. What I'd like you to do right now is take out your calculator and graph both of these functions that I have up on the board. F of x is equal to x cubed minus 4x squared minus 5x minus 3. And g of x is simply x cubed. Go ahead and graph those on your calculator. When you graph those two equations on the same graph, you're going to get a graph that looks similar to this. You might have a slightly different window, but that's okay. It should look something like that if you're zoomed in fairly close. Now, what I would like you to do is I'd like you to zoom out a little bit. Now your graph is going to look something close to this. Go ahead and zoom out maybe 1 or 2 more times until the two graphs look almost identical. Here on this third graph, you can see that my two graphs look very, very close to being the same thing. Now, what this indicates is that my leading term, that of x cubed, and here of x cubed, have a lot to do with the way the graph looks. So, having learned what we've learned so far, let's see if we can describe the end behavior as I reach negative infinity on my x and as I go toward positive infinity on my x, based on the equation alone. I don't want you to graph it. It's okay if you do, but I want you to answer the question without graphing it. And then you can take some time, graph it, and see if your conclusion is correct. Well, as our x reaches toward infinity, my y value is also going to go closer and closer to infinity. As my x goes toward negative infinity, my y value is also going to go toward negative infinity. They're going in opposite directions because my function is an odd function. It's x cubed. And so they're going to be coming and leaving in different directions. Since I have a positive value for my coefficient of my x cubed term, that means I'm going to be coming in from the negative direction, and I'll be leaving toward the positive direction. Let's try another one. Let's see if we can describe the behavior of this. Now, this function is 2x to the fourth. So since this is an even function, it is going to be leaving and coming in from the same direction. In this particular case, since I have a positive value, as I come in and as I leave, I will be going toward infinity. So if I use negative values of x, so very large negative values of x, I'm going to be coming in from a very high positive value of y. If I use positive values of x, I'm going to be coming in from positive y. Graphing the second function, you can see I'm coming in from the positive and leaving out toward the positive as well. So let's discuss the zeros of polynomial functions. Remember that zeros are the locations whereby my graph is going to cross the x-axis, which means my y value is equal to 0. So f of x is going to be equal to 0 at those points. Zeros can be found by factoring. So yes, we can graph the function and find the zeros that way, but in some cases we can also do it by factoring. So let's see if we can factor this polynomial into binomials to where we can find where our zeros are. The first thing I want to look for is a common factor. If I can factor out that common factor, it's going to make the rest of the factoring a little bit easier. And indeed, I can factor out the value of x here. So that's what I do first. So I have x times the quantity x squared minus x minus 6. Now what I'm going to do is I'm going to try to do the reverse FOIL method on this x squared minus x minus 6 piece. I look at my last term, it's a negative. That tells me I'm going to have a positive and a negative as the two signs inside my binomials. Factors of x squared are only x and x. So that means I'm going to have an x plus something and an x minus something. My factors of 6 are 1 and 6, 2 and 3. I'm going to use the 2 and the 3. I need more negatives than I do positives because my middle term is a negative. So that means I'm going to put the negative sign with the 3 and the positive sign with the 2. If I try to FOIL that back out, I do indeed get back up to the previous line. So that is the correct factorization of it. And now my zeros are located at 3 and negative 2. If I were to graph it, this is the way it would look graphed. Repeated zeros can also be found in certain polynomials. So for instance, if I were to factor a polynomial and I were to get something like the quantity x minus 2 cubed times x plus 1 squared, that means I have repeats. This particular term, this x minus 2, is repeated 3 times. So 3 of my zeros all are located at 2. 2 of my zeros are located at negative 1. So this is what we call a multiplicity. We have multiple answers in the same polynomial. Here we have this particular polynomial graphed, and you can see a little bit of difference between the two. Notice that at negative 1, my graph goes up, touches the line, but then starts coming back down. Whereas if 2, my graph goes up, hits 2, and then continues on going in a positive direction. So here's what we can get out of this. Multiplicities that are odd will cross over my x-axis. Multiplicities that are even will be tangent to my x-axis. So if they're odd, they go through. If they're even, they touch and come back the way they were coming from. So now let's take all of this and see if we can answer some simple questions based on some of these polynomials. The first polynomial is the quantity x plus 2 cubed times x minus 1 cubed. First question is, what is the degree of this polynomial? If you answered 5, you are correct. We get that 5 from the third degree here and the second degree here. So if I were to distribute all of these, if I add those two together, I would get an answer of 5. So I have 5 answers, 5 zeros that are possible with this polynomial function. The next question I have for you is, what are the zeros? In this particular case, we only have 2 zeros. One is located at -2 and the other one at a +1. What is the multiplicity of each of those zeros? The multiplicity of the -2, since it is cubed, is 3. The multiplicity of the +1 is squared, so it is a multiplicity of 2. What zeros cross the axis and which ones simply touch the axis and then leave the same direction? So which ones are tangent? Well, remember, the odds are the ones that cross over. The evens are the ones that only touch. So it's going to cross over at -2, and it's only going to touch at the +1 value. So that concludes our lesson for today. We talked about polynomial functions, the degree, and also the end behaviors, and how we can find the zeros. Much of this will be beneficial for you as you look toward taking the test and looking at polynomial functions. If you know some of these basic concepts of polynomial functions, you will be able to answer many of the questions much more quickly.